Hi, everyone, and welcome to this edition of PriSC 2022. Thanks to all of the people who are joining us both remotely and in person. We are relying on an extraordinary team of student volunteers, so thanks to them, everything will run smoothly today. The first session of the day is a keynote, and it's a triple header. We have Piotr, Benedict, and Daniel, who will give us a keynote on BPF and Spectre. The stage is yours.
Thanks a lot. Hello and welcome, everyone. So the talk will be about BPF and Spectre and how we, what kind of attacks are there and how we mitigate them. First off, I will start a little bit as an introduction in terms of what is BPF and how the BPF verifier works, and then we will move over to speculative execution and side channels, and finally we combine all together by showing some of the attacks and mitigation we've been working on. And then we conclude with the question and answer session. So what is BPF? So BPF is basically a framework where you can extend the operating system kernel. You can think of it as a general purpose engine with a minimal instruction set. The goal basically has been twofold. One is to have a ideal mapping of instructions from BPF to x86 and ARM64 in particular, and also minimal instruction set because it has to be verifiable in the kernel. So it basically allows programs to customize the kernel behavior. That means you can change the behavior without having to change the kernel source code, without having to reboot or update your kernel, and in particular also without crashing the kernel. There are a couple of use cases that come along with BPF and that have been quite popular in the recent years. One is networking. For example, you can implement denial of service protection with BPF. You can attach BPF programs directly into the driver of a network card at the so-called XDP layer. And then it can handle millions of packets per second and can drop them efficiently, or it can forward them. So it can also be used to implement load balancers and gateways or firewalls. It also helps to reduce the attack surface of the host because you can drop packets or bad packets as early as possible. You can customize your host stack. For example, if you think of Kubernetes container orchestration, BPF allows for an efficient way to do all the networking there. BPF has also gained popularity in the security space. For example, Linux security modules, they can be implemented through BPF these days, and it has a lot of popularity in terms of tracing and application profiling. So you can regard BPF as a kind of new type of software, if you will. If you compare that to regular user applications and the kernel, BPF, so while the kernel has direct access to the hardware, BPF basically has access through restricted helpers, but still runs in kernel space, whereas user applications, they typically have to access through system calls. User applications, they can segfault on an error, kernel can panic. However, BPF programs, they must not destabilize the system in any way. And they are also more secure because with the kernel, if you implement code in the kernel, you have basically no protections whatsoever. Whereas BPF programs, they are verified when they are loaded into the kernel, and they allow for user-defined custom programs under good performance. Just to help you understand a bit the state model of BPF, so basically an orchestration system will load and attach the BPF programs to a specific event, for example, in the kernel, let's say, for example, trace point. When that function gets executed, in other words, when an event fires, then it goes to the on-CPU state where the program gets executed. Once the program ended, it's becoming inactive again. The BPF program can access the kernel through helpers. There are some BPF programs where spin locks are allowed, so they can go into a spinning state. And there's also some restricted state for some type of BPF programs where they allow to sleep. Now going to the BPF verifier. Basically, an application loads the BPF program, those BPF instructions into the kernel. The kernel makes a copy of them and then verifies that in-kernel copy of BPF instructions through a static code analyzer. That has to ensure that the programs terminate. So there's a first traversal of the program to make sure it's a DAG. The BPF, the verifier prevents unbounded loops, so it will then reject the program when they cannot be verified, and it also has, of course, to prevent out-of-bound or malformed jumps. The verifier has to ensure memory safety, so you cannot just access kernel memory out of bounds and mess around with it. The verifier prevents use after free bugs and object leaks. For example, if a specific helper takes a reference count on some kernel object, the verifier makes sure that there's a corresponding kernel helper function called to release that reference count again. And it also mitigates vulnerabilities in the underlying hardware, such as Spectre, which we will see later in that talk. Verifier has to ensure type safety in order to prevent type confusion bugs. For example, there are different types of programs. They can all access different types of helper functions. They cannot be executed in a way where you would then, for example, corrupt kernel memory through that. There's also something called BPF type format, or BTF in other words, which is, for example, used in tracing, where it helps the verifier to recognize BPF kernel data structures and then use that BTF type format in order to make sure that those aggregate types, such as structs, that they are not accessed out of bounds. And last but not least, it also has to prevent from hardware exceptions, such as divisions by zeros. For example, in case a given register has a known scalar, it will be rejected if there's a divide by zero detected, but if it cannot be detected at verification time, then the verifier will basically rewrite those instructions to generally follow the ARM64 spec, where you don't have where you don't throw exceptions. The verifier basically works by simulating all execution paths of the program. That means it has to follow the control flow graph. So for each instruction, it computes a set of possible states. States here, they relate to the BPF register set. So there are 11 BPF registers, and there's also BPF private stack that the program can use. It has to perform safety checks depending on the current instructions. For example, if you have a memory load, the verifier has to make sure that it has the correct type, it's not out of bounds, and so on. And it also tracks register spill and fills to the private BPF stack. There can be back edges in the control flow graph, so that's not forbidden by itself, but the verifier will basically try to brute force simulate those bounded loops. And well, if they surpass a given threshold where it's like too complex or there will be too many states for the verifier to handle, and it will reject the program. Of course, with that, there comes the problem of dealing with a large number of states. In order to help with that, the verifier implements path pruning logic, where it compares the current simulated path to the prior executed simulated paths that had a safe exit. So it will check whether those paths are in that sense equivalent and whether they can then be pruned and skipped in terms of verification. The verifier implements function by function verification for drastically reducing the state that needs to be tracked. So it will basically split functions that can be called from BPF. They will basically be verified first, and then you have a set of input and output constraints. And then later the main program will not go through the whole function again. It will just check whether whether everything is proper in terms of those states for the entry and exit. And there's a on-demand scalar precision tracking in order to reduce state. So the verifier will basically try to first gather less information so that it will help the pruning of the paths, and only if really needed. So for example, if there's a register where that is passed to a helper function, and that register, for example, contains a given length that is needed in order to verify a memory area in terms of out of bounds access, then it will go back and find the actual concrete value of that register. And once the a certain threshold has been reached where it would be too complex to verify the program, which is in these days in the kernel 1 million BPF instructions. Or if there's too many state that had to be accumulated, then it will also reject the program. Just to give you a short overview in terms of how the register state tracking works. So the BPF register typically has a type that can be uninitialized, or it can be a scalar type or given pointers. They can also be composable. For example, pointers, they can potentially be null. The register has an ID. That ID that helps in particular for state propagation. For example, if you do a null check, it can propagate that the register, like for a given path, is not null also to the other registers with the same ID. It has a fixed part of a pointer offset, and it has a so-called tristate number, which represents knowledge of the actual known and unknown bits of the register. And then we have 64 and 32-bit signed and unsigned bounds. They're basically coupled together with the tri-state number, and they hold a lower and upper bound of the unknown value. And they are basically used to determine whether a memory access with that register will result in a bad access or not. So just to give you a short introduction to the tri-state numbers, because they're quite interesting. Basically, they contain a value and a mask, both 64-bit. And for each bit position, if the mask has a value of 0, then basically they represent knowledge. So they represent either that the actual value will be 0 or 1. But if the mask has a value of 1, it will represent an unknown bit. So for example, if you have like a small toy example of a 4-bit TNUM of a 010x, they can basically be composed into a 0100 value and a 0001 mask, and that represents a decimal number of 4 and 5. Of course, if all the bits are unknown, then that represents from 0, like a set from 0 to 15. Those TNUMs and the 64 and 32 boundaries, they basically go hand in hand. So the verifier propagates and refines the knowledge between them, and they are both needed. So in the example state below, you can see that you have more information about the potential register value together with the bounds as if you would have it only by the tri-state number itself. There can be arithmetic performed with the help of tri-state numbers. For example, on the left side here, you can see the addition operation that is implemented inside the kernel. And if you look at the 4-bit example again, you will see that unknown bits, they basically propagate further with the carry, and the resulting set of possible values, they are not perfect in the sense that they only contain the the exact result, but they also have some uncertain numbers. But it's in the end like a superset. Same for the multiplication, and I can refer you here to a paper from Vishwanathan and others where they refined the multiplication algorithm inside the kernel to be basically more precise than it was originally, so that basically the number of the unrelated values in the result, they are minimized. Just to provide a small toy example, we have a structure and we have a write to the array inside that structure that will result in the following BPF bytecode that you can see here on the right side. And if we go through the verifier, of course, in a simplified way here, just to provide an example, at the beginning are 0 points basically to a map value pointer that holds this structure, and it has a maximum value size of 1032 byte. Then we load the index into another register, into R1. We know that the maximum unsigned value has to be 255 because it's a 1-byte load. Next, we load the value from that structure into another register, R2. Same story, we have a 4-byte load here, so everything is unknown except the upper bound of the 4-byte. Then we add the offset until we reach the location of the array. Then the verifier will see that there's a fixed offset on the pointer, and then we multiply the array slot size with R1. What you can see here, the maximum value change from 255 to 1020, and also the tristate information change because we have a stride of 4 bytes. And what you can see next, we basically added that offset to the pointer. So the pointer also holds this information now for the dynamic offset. Then there are two value which we want to store into that array location is basically negated here. To simplify the verifier, if it's negated, the verifier will just say it's an unknown value. And then later on, the actual store will happen to that array offset. And the verifier concluded it's safe for all the simulated values on R2. There are a number of challenges for the verifier, especially if it's exposed to non-root users. It has been an attractive target for exploitation simply because the verifier is growing in terms of complexity. And once you hit a bug, you can basically then, in the worst case, bypass OS mitigations. The reasoning about verifier correctness is non-trivial, especially then when it comes to also Spectre mitigations. It only has been partially formally verified. I mentioned earlier the tristate numbers. Also, there has been formal verification done on the just-in-time compiler in the kernel. There are occasions where valid programs get rejected. So the LVM compiled objects, they basically have, in that sense, a disconnect in terms of the context of the optimizations done. So the verifier has to try and understand them, but there are still restrictions, of course. There's a so-called stable API for BPF programs with some limitations with tracing, meaning once you load a BPF program in production, for example, your load balancer, it should not just break and get rejected by the verifier when you upgrade the kernel. And there are performance versus security considerations. Like in one aspect here that is worth to mention, the verification of complex programs. It has to be efficient to be practical. It just has to take maximum, not more than a second or two to load the program into the kernel, but not minutes. Then nobody would use it, right? Same with the mitigations. So if there are security mitigations, they have to be practical because the performance of BPF programs are crucial. When you have load balancers that would handle tens of millions of packets per second, it cannot slow down everything. Another challenge, the complexity of the verifier got increased quite heavily with the 32 and 64-bit operations. And of course, it's BPF in the kernel and also outside of the kernel is an active community, a growing community. So there are more features. So, the security still has to be present there. And now I will switch to Piotr for the speculative execution part.
Thanks, Daniel, and welcome everybody. So I hope you can see my screen. The bulk of this presentation is about speculative execution. So let's start with why hardware uses it and if we should expect it to stay with us. Iron law of processor performance gives us some formula for how much time program takes to execute. And it's essentially how many instructions are to be executed, how many cycles each instruction take, and then time for each cycle. The number of instructions depends on what the program source code is, what is the compiler technology, and instruction set architecture. Instruction set architecture also affects how many cycles each instruction takes. Finally, what we are going to talk about is microarchitecture that affects both how many cycles instruction take and how fast the hardware is. We also have fabrication technology that determines the performance of the hardware. Looking at the following graph, we can see what is the contribution for the microarchitecture optimizations over the years. And what is interesting about it is that while in mid-80s, we could see that it usually takes a few cycles for each instruction to execute, by 2000, it appears that processors can execute multiple instructions each cycle. So this is an interesting optimization. And the way it works is that instruction-level parallelism can be exploited such that hardware can execute independent instructions in parallel. It's even possible for out-of-order execution to happen when the input data and hardware resources became available. And the way it's done by the modern hardware, it's essentially variants of old Tomasulo algorithm that was originally used by IBM in 1960. So it's like a very old technology. I'm not going to go into the details, but the basic idea is that hardware can track multiple in-flight instructions, and then dependencies between those instructions are tracked using the data flow. So in the following example, we can see the first two instructions could execute immediately because all the registers values are available, while R4 and R5 are going to block the remaining instructions. The third instruction, which loads from memory, can be quite slow, and so the fourth instruction can be actually the last one to execute, which means that the R8 may be executed maybe a bit much earlier. Hardware essentially tracks dependencies and executes things as soon as possible. In order to maintain the illusion that program executes in the normal order, that those partial results, the temporal results, are committed in the program order. There are certain challenges that are relevant to our work with parallel execution. Those include control dependencies and ambiguous memory dependencies. Control dependencies are where conditional and indirect branch instructions determine what to execute next, and they occur frequently in typical programs. It means that the opportunity for parallelism is limited. However, it's possible to quite accurately predict outcome of those branches, and then we could roll back on this prediction. And so universally, it's exploited to significantly increase gains from parallel execution. For ambiguous memory dependencies, the program semantics determines that load should depend on the preceding store, and this dependency exists only when accessing the same memory location. However, in order to disambiguate this dependency, we need to understand, we need to know the addresses of the memory access. Those addresses are usually computed indirectly, and so it's very common that they could cause some delays. So what hardware can do? If we look at the following program, we have store that uses R11, and then the last instruction is load using R5. It may be quite slow to determine if R5 and R11 are in fact overlapping, because R11 in this case is loaded from memory, and the memory can be very slow. And so hardware could, in fact, start to execute load just assuming that R5 is different than R11, they don't overlap. And if it's wrong, just roll back. It is used in practice, for example, by Intel microprocessors, where architecture optimization reference manual describes essentially this technique. The details are not really documented. However, with testing, we were able to determine that this speculation is controlled via predictor, and some details of those algorithms of this prediction are actually used by in our work. What is important to understand is that when doing the rollback from this prediction, the rollback is limited to architectural state that is visible. It is, in fact, I could argue, not practical to extend to microarchitectural state. For example, because predictors are usually guided by the past behavior, and they sort of provide some memory. How the issues could be exploited? For example, we have speculative store bypass, where we can train memory disambiguator such that it will proceed with the load, it will complete the load instruction under speculation, even before the store addresses are known. The rolled result could be then used to modify microarchitectural state that is still under speculation. And finally, after the CPU realizes that load depends on the store and rollbacks the state, we could still extract this microarchitectural state through side channels. Is it possible to disable the speculations? Yes, but it costs performance. And so hardware vendors simply provide the mechanism, and then software developers has to make the choice. For example, in case of the discussed vulnerability, the speculative store bypass, the 886 instruction set provides elfence instruction that essentially stop all younger instructions from execution until all precede store addresses are resolved. There may be other mechanisms, for example, CPU configuration registers that could permanently disable speculation for this case. What are the common patterns in speculative execution vulnerabilities? Usually, we have hardware that relies on probabilistic methods to break dependencies, and this is required to maximize performance. The microarchitectural state affects the microarchitectural state is affected, for example, as discussed, to track the prediction accuracy, and this is in fact not fixable. And finally, we have side channels that can be used to extract the state using variety of high resolution timers. Shall we expect vendors to stop speculation? I would say no. And in fact, we still see that vendors continue to innovate in order to maximize the benefits of parallelism, which means that software needs to accommodate, and we can expect the speculation to stay with us. So at this point, I will stop sharing, and I will let Daniel to continue.
Well, I will continue. A warm welcome also from me. Should be able to see the slides right now. And we will get a quick step back and talk about the microarchitecture. Like the instruction set architecture is fixed, and to gain advantages against competitors, the modern process designers like Intel and AMD have come up with microarchitectural improvements which aren't standardized in the instruction set architecture. And for example, here on the right, you can see the Intel Core 2 architecture, which consists of the decoding phase, the reordering phase, the execution units in yellow, and the I/O units in green. Now, these microarchitectural optimization include, for example, branch prediction. And in the branch prediction, the CPU tries to predict the outcome of branches if the comparison before is not known due to because, for example, the computation took a long time, so the CPU speculates about the outcome and jumps accordingly. And another form of microarchitectural optimization is out-of-order execution. When we have, for example, a slow load operation, the pipeline would usually stall and wait for the load operation to be finished. However, to prevent it and to gain some performance improvements, modern CPUs are able to execute instructions out of order. And lastly, we have the speculative execution, where the branch prediction is a part of, but the CPU does not only speculate on the outcome of branches, it can also speculate about, for example, memory dependencies, for example, a read after write, write after read dependency, and so on. And if the prediction is correct, the CPU just commits the speculated window. However, in case that the speculation is wrong, the old CPU state has to be recovered, and this is done through resetting the register state to the pre-speculative state and discarding all memory writes which are buffered in the memory ordering buffer. However, cache modifications aren't restored, so all transient load instructions influence the CPU state in a way which we can use later to obtain side channel information. Now, a quick recap on the cache architecture. As you can see, we have here the L1 cache, the L2 cache, and the L3 cache. And the L1 and L2 cache is usually core exclusive, while the L3 cache is shared between a core complex. And the L1 cache, to access the L1 cache, it takes roughly 4 cycles, which translates to 1 nanosecond. The L2 cache needs 12 cycles, and the L3 cache needs around 38 cycles. Now, if we dereference a pointer and access the memory region, we can simply, by taking the time, guess whether the element was in the L1, L2, or L3 cache, or even in main memory. We do it by using a hardware timer, like here's a RTD-SC instruction, accessing the memory, taking the time again, and computing the time delta. Now, this can be used as a side channel, and in the BPF program, it's a bit more challenging because we aren't allowed to use plain assembly instructions, so we have to find another way. And in eBPF, we have a leaker program, and first of all, we dereference the desired memory location, where the value which we want to leak stands. For example, under speculation, the memory pointer might point to an arbitrary location where we haven't access to. And when we dereference that pointer, we obtain the value. In the next step, we apply a bit mask to our value and leak the value, the bits of the value bit by bit. And we're multiplying the bit with hex 100. And in the end, we will access the array element either at the position hex 300 if the corresponding bit was set, or at the position hex 200 if the corresponding bit was not set. Now, we have to the leaker block, we have a corresponding reader program, and we basically doing the same as seen on the previous slide. So we're taking the time, but not with the hardware timer. Rather, we use a BPF helper function, so, the function k-time get nanoseconds, access the memory location, and then we compute the time delta again. Now, with the time delta, we can make assumptions whether the value was in cache or not. And so we can leak the elements or the bits of the value one by one. So the MSB is here 0, and we can go through it bit by bit. Now, obviously, we have to make sure that the map value is not in cache if we first start the leaker proc. So between different runs of leaker and reader proc, we have to make sure that the cache lines are bounced so that all map elements, especially the map element at the position hex 200 and hex 300, aren't in the cache. Usually, we would use the cflush instruction for it, but eBPF doesn't allow us to execute arbitrary assembly instructions, so we have to come up with another mechanism, and we use so-called cache line bouncing, and we simply access the map element from another core, forcing the value to be loaded into the last level cache and being erased from the L1 and L2 cache. Now, Spectre isn't related to eBPF specifically. It's a class of hardware bugs, and it affects all programs which will run on the buggy hardware. However, Spectre and eBPF is particularly interesting because usually with Spectre, you cannot cross privilege boundaries. It's unlike Meltdown, where you can attack the kernel. Spectre only works in the current address space. However, eBPF programs run within the kernel, and it is possible to load eBPF programs as an unprivileged user. Thus, we can use Spectre and eBPF in combination to cross the privilege boundary of the kernel and leak kernel memory. And specifically, we will talk about Spectre V1, V2, and V4 and the countermeasures the verifier applies and how to mitigate it. Now, the simplest exploit is the Spectre V1 exploit, also known as bounce check bypass. And here we simply rely on the branch predictor to mispredict branches and execute instructions speculatively out of order and leak memory. Now, the branch predictor relies on a construct called the pattern history table. And on the left-hand side, you see a picture which shows such a pattern history table. And the pattern history table has as key entry the lower 5 bits of the branch. And the value is a 2-bit state machine or counter, which signals if the branch is likely or unlikely to be taken or not. Now, obviously, the pattern history table isn't perfect. So we have collusions, as you can see here, with only 5 bits. And especially in the beginning of a loop, the PhD could contain wrong entries or guesses. Now, how does such an attack looks for a BPF program? Now, here we have a simple program where we set the register 4 to register 10, where register 10 is the base pointer, which points to a 512 bytes stack location, which we can use in our eBPF program to store arbitrary data. And we subtract 1. And we will set in the third line the stack location at minus 512 to 0. Now we load 2 attacker-controlled values in register 2 and register 3 and mask the value in register 3 with 1 and 2, which will make it a known 0. And afterwards, we subtract 11. Now, the if 511. In the if condition, we check if register 2 is equal to minus 511. If so, we execute the second the instruction where we subtract 511 from register 4 and access the stack at index 512 and read out the 0 we previously wrote. However, if it's unequal to register 3 and the CPU mispredicts that branch, we would add an arbitrary value to register 4 and dereference arbitrary memory. Well, it's pretty easy to prevent in that case, since we will access the memory at a predefined constant, which we will know at compile time. So what the verifier does is simply rewrites the instruction from relying on an unsafe user-controlled register to a special register, which is the register R11, which contains the constant offset, which is then added at runtime to the pointer for a safe dereference. Now, what happens if the offset is not known and is, for example, not a constant, but lies in between 0 and 32? Now, there has been invented a de facto standard masking scheme for Spectre V1, which is not only applied to eBPF, but all over through the Linux kernel and at the critical locations, obviously, not at every if branch. And this masking scheme might look really confusing if you haven't seen it before, but we'll quickly go through it. Consider the case where our value is in bounds. So the attacker-controlled value is here 31, which is below 32. And as you can see, after the masking has been applied, we will add to our register R4 the value 31. So it works as expected. Now, in the other case, where the value is out of bounds, you will see that we will add a 0 to our memory pointer. And this is mainly because here the bit mask is now contains only zeros, while in the valid case, the bit mask only contains ones. Now, the verifier mitigates the Spectre V1 exploit mainly by tracking the pointer limits, rewriting the pointer arithmetic, and spawning a new path for verification where we do not modify the memory pointer at all. Otherwise, it would be possible to do another Spectre attack right below it. Now we come to the most interesting part. It's a pointer type confusion attack, where the root cause is mainly from Spectre V1. And this attack was also presented at the Usenix 2021 conference. And the paper which introduced it got awarded with the Best Paper Award. And they also won the prize from Meta, worth $100,000. So it's really interesting, but the basic concept is fairly simple. We have 2 mutually exclusive paths. So register 0 can't be equal to 0 and 1 at the same time. So the verifier assumes that instruction 3 and instruction 5 will never be executed on the same execution path. However, if we were able to mistrain the branch predictor, and we are able to mistrain the branch predictor, we can trick the CPU to speculatively execute instructions 3 and 5 on the same path. And this results in an arbitrary memory dereference at a scalar value which the attacker can control. And the misprediction is done through the pattern history table poisoning, as we've seen previously. Now, to mitigate this attack, the verifier is not allowed to make any assumptions if a branch is taken or not. So basically, the verifier is not allowed to prune any unreachable path. And here we have again the consideration, do we want more security or do we want more safety? And now Daniel will continue.
So in fact, I will take over. Okay, you should see my screen. I will skip Spectre version 2 because of timing. So we don't have much time, and I would like to have some time left for questions. And let's just jump to Spectre version 4. So what I was already talking about, this is just a short reminder. The memorydisambiguation is about like how to determine if load depends on the previous source. And the way it works is that when we have this, when the load address was already used by some store instructions, the disambiguator tries to determine, the issue is about the ambiguous dependencies between the load and the previous stores. So in order to increase the level of parallelism, the disambiguation happens where a load may proceed even if store addresses are not known. And the attack is how we can trigger this mispeculation is such that the load could execute ahead of the dependent older stores, and then we could use the gadget to read the data and just leak it. So what happens here is that we may have a store instruction that is high latency. Usually it's when memory address takes some time to compute. And then we may have read that can execute ahead. This creates this leads to unsafe reordering of the instructions, then break program semantics under speculation. It only happens under speculation, and then the hardware recovers. However, microarchitectural state is affected. So we have an example of such a program. What happens here is that we are using a stack. We are using the stack to store value of the R2 register, which could be arbitrary scalar. We then copy the value of the stack pointer to another register, train the disambiguator. This is essentially unrolled memory copy that I just, for brevity, skipped here. We call a dummy helper function. We spill valid map pointer to the same stack location where we already stored our scalar. And finally, we read from stack and access memory. So what happens here is that this allows us to actually read the value, the memory location we shouldn't be able to. And without speculation, the read would happen from R7, which is just the map value. However, under speculation, it's possible for it to happen from the scalar. That could be arbitrary memory location. What actually happens here is that when we use the BPF ring buffer output helper, it internally pushes some registers on the stack, including R10, while R9 stays in hardware register. Once the helper subroutine finishes, the R10 may still not be available because it has to be read from memory, from the stack. And when hardware executes the store, when hardware executes stores and loads, it cannot just proceed with store. It decides to go with load, which means that it reads the stale memory value that we already wrote. When working on mitigation for this vulnerability, we discussed a number of different options. And actually discovered another variant of the same attack that does not really require the BPF ring buffer helper, which is quite interesting. It also shows how it's important to talk over the details and understand and fully understand what really happens. So the second case is when we start with training the memory disambiguator. It's again the same sort of unrolled memory copy. We store arbitrary scalar on the stack. We then perform some memory stores, roughly 30 instructions. We still valid map value pointer to the stack, and then we do the same thing as before. So we just read the stack location and then access memory using the read value. Without speculation, this would read from our safe memory, our safe map value. However, it may happen that the load proceeds before store, and this allows for us to read from arbitrary memory address. So what happened here? Why did we speculate? In fact, we sort of scratched our heads because it's not really obvious. And to be honest, we are not 100% sure that we understood it in detail. However, the Intel optimization manuals give us some hint. So what we have here is the diagram of what Ice Lake microarchitecture looks like. It includes number of ports. The functions of these ports are described in another table, and it essentially says that loads are used are executing on the dedicated ports, while store addresses are computed on completely different hardware units. So what we think happens is that when the scheduler keeps track of the execution, it can just execute some of the store addresses, essentially utilizing all the available store address resources. Additional instructions get loaded at the same time. Some of them may be waiting for the available store ports. And then we get to our load. But since the load port is available, we didn't have much loads before because all the instructions were stores. Hardware is free to pick it for execution. And because of our disambiguation training, the load is allowed to complete. The value could be used for by another instruction, while the preceding store is bypassed. So in order to mitigate it, we decided to use alphas instruction, and this is exposed through a dedicated BPF instruction. What we do is the BPF verifier observes how the pointers are still on the BPF stack, and also checks for the first use of BPF stack slot. That was another vulnerability that we discovered at the same time. And it inserts no-spec this new instruction after relevant stores, such that whenever the compiled code executes, the GTA compiled code executes, x86 hardware essentially runs the alphas instructions, ensuring that none of the loads can proceed until all the store addresses are resolved. This addresses the vulnerability. So at this point, I will stop sharing and let Daniel to continue with the conclusions.
All right, I will really quickly talk about the relation to process capabilities and then conclude. So for privileged BPF, which means root programs, which are, for example, used in kernel tracing, like the tracing already has to access kernel memory. So there it doesn't make sense to apply all the mitigations, but only the Spectre V2 mitigations, which we didn't cover here. But basically, there it's either using the red Pauline or to avoid it completely by rewriting an indirect call into a direct call. And it has, that's privileged BPF is used in the vast majority of BPF projects. And it's generally, the overhead is very little, so it has very little practical impact. For unprivileged BPF, which is disabled by default these days, all the mitigations are applied transparently, and the performance impact depends on what, like how the program is written, what mitigations are involved. To summarize, BPF runtime basically applies to Spectre V1, V2, and V4 mitigations. The mitigations such as load hardening, they also help with non-Spectre attacks to basically harden the BPF verifier, and they are applied in addition to the mitigations that are already enforced by the kernel. So the BPF verifier partially performs deeper static analysis than compilers. One example here is like the speculative path analysis that we have. The verifier also eliminates speculation possibilities when it's possible. As you saw earlier, what Benedict presented, the rewrite with the constant offset instead of a register-based offset. And it also allows to transform indirect jumps into direct jumps for the Spectre V2, so that red polyns can be avoided. And last but not least, the BPF verifier applies the mitigations for V4 only when necessary. So when, for example, pointer spill fills for the stack under, let's say, LVM register pressure have been observed, or the very initial BPF stack usage to prevent leaking from prior data on the stack. Some future work, so BPF, like the core BPF, is not perfect yet in terms of verifiability. So only a few constructs have been formally verified. However, like the research community, interest from the research community is around BPF is definitely increasing. What we see, some operations such as the division on TNAMs are not range tracked. Just to mention another example, in that case, for example, registers are completely set to an unknown state. There has been recently published work to improve the multiplication tracking on the verifier that I mentioned earlier. So the TNAM multiplication now holds more precise information. The addition, subtraction, multiplication has been formally proven. And the other issue that should improve in future is like to better formalize and document the current verifier procedures, also in the context of Spectre, for example. So right now there's not much documentation out there how the verifier operates internally, except that you have to go and read the source code. So it's sometimes challenging to get an overview. And with that said, we want to conclude our presentation and open up for questions. Thanks a lot.
Thank you. All right, and now it's time for questions. People who are watching online through AirMeet can ask their questions through the Q&A tab, and anyone attending can upvote questions if you want to steer the discussion one way or another. Do we have any questions in the room? All right, so I'll open up with a first question while some more questions come up online. A lot of the initial part of the discussion, of course, as a programming languages person, spurred a very natural question, which is, what if some of this was written in a more restricted language to begin with? Like, could some of the ideas from WebAssembly be reused for all of the process isolation and all of the avoidance of out of bounds or irregular memory accesses?
So I personally haven't looked too much into WebAssembly. However, I would think that the BPF instruction set is probably smaller, like less complex than that. But yeah, I cannot give you a definite answer on that.
All right. We have another question from online. Whichever, like any of them, just pick any of them, please. All right, question from Kathleen. All right, so the speakers should be able to see the question on the screen. Who wants to pick it up?
Maybe I will try to answer it. So the question is whether formal verification of the Spectre mitigations for BPF verification would be interesting. Well, actually, its conclusion is just like a state of fact. And what would be the good security property to target? What arbitrary memory access is not that arbitrary memory access is not accessed? I would say yes, definitely. It's very interesting for the formal verification, especially because like manual human sort of trying to understand what's going on is very difficult. You have to work on a few different levels. You have to understand how the BPF program works. You have to understand how the program that verifies the BPF program works, etc. That said, there is definitely good amount of work to be done. As I tried to show, it's probably going to happen for the foreseeable future that we're going to see those vulnerabilities. The good security properties to target, I would say, are both for the control flow and for the memory disambiguation. Probably memory disambiguation is sort of more, I would say, difficult and probably also more interesting because of how it affects various programs. With control flow, you can essentially, like, you can have very cheap sort of constructions where you could just insert them and then you are sort of free from them. But with memory disambiguation, it's like essential, like very sort of costly to disable the disambiguator completely, while very difficult to sort of prevent them. So I would say definitely memory disambiguation.
Cool. Next most upvoted question, please. That is not the most upvoted question. Yes, thank you.
No, maybe I can answer it. Speaking for myself, Piotr and I were mostly the attackers, so we didn't try to validate any countermeasures. Obviously, we have proof of concept codes, which are also publicly available. So if you're interested, you can definitely take a look. And the complexity mainly arises through the proprietary algorithms which Intel and AMD are using inside the CPU. So that's the black box where we aren't sure what's actually happening within the CPU. And we performed some tests and observed that it's possible to use it as a side channel. But I guess to better understand it, we have to sign an NDA and ask Intel and AMD what's actually happening.
Okay, thank you. Next question.
I can take it. So BPF is compatible across Linux, BSD, Windows, and RISC-V processors. Do you think the attack and defense is transferable to these ESA operating systems immediately? So right now, so basically what I mentioned earlier, like, so BPF is here in terms of eBPF. So the eBPF aspect on FreeBSD, I think it's present to some degree on FreeBSD. On Windows, it's being worked on. They should definitely work there as well. The defenses should also be, like, could be implemented in a similar way. So I think, yes, it would be transferable.
All right, so that's a yes. I think we have time for maybe one more question.
Okay, so I can take that as well. Given that BPF is only partially verified, what would be the next interesting part of the BPF toolchain that you would like to see verified? I think definitely the area of tnums to complete that work would be really interesting, and as well the relation of the tnums together with the bounds, like a lot of complexity in the verifier where we've also seen security bugs happening, or in particular on the 64 and 32-bit bound handling and basically the transfer of this information together with the tnum. I think that would be an exciting place to look deeper into for the formal verification.
All right, so I think we have time to get to the question from Santosh as the final question. Yep.
Do you want me to take this as well? I think I
guess you have the best position.
So there's some discussion about an offline verifier rather than an in-production verifier. What are the pros and cons? So in terms of, I'm not quite sure, in terms of offline verifier, you mean that it's verified outside of the context of the kernel, I would assume. And I think, well, I mean, there have been different approaches. For example, at the Linux Plumbers conference, there was a talk where someone from the research community basically embedded the proof into the program itself, which was quite interesting. So there are definitely concepts that could be potential to maybe even replace the current in-kernel verifier, but so far what some of the challenges that we've seen there when in discussions are that right now they wouldn't be able to handle complex programs in a sufficient time. So it would take more than, like for that particular example, I think it was more than like 30 minutes to verify more complicated programs. So that's definitely a challenge that would have to be taken into consideration.
All right, then I think that's it for questions. So let's thank the keynote speakers again.